about a project that I built along with a remote team called SpaceCraft. Before I get started, can everyone hear me? Okay? Okay, cool. So my name is Julius, and I recently moved to New York. I've been a freelance full-stack developer for the past 2 years, and over the past year, I've been working on the project I'm going to be talking to you all about tonight, SpaceCraft, which, like I said, I developed with a remote team of just open source contributors, and the talk is about building a real-time collaborative REPL. And so to start off, I'm going to talk to you about what SpaceCraft is. And like I said in the title, SpaceCraft is a open source real-time collaborative REPL, Read-Eval-Print-Loop. And basically what this project does is it allows users to write and execute Ruby, JavaScript, or Python code in the browser, which are the 3 languages we currently support. It's built with Node.js and WebSockets, and is deployed via Docker. And the point of the project is to encourage pair programming amongst remote collaborators without having to undergo any kind of setup you would normally have to do when you're downloading any kind of new language you'd like to try out. And so before I go into the details of how we built it, I'm just going to give a quick demo of what it looks like. Okay. So here we have the project. And you can see that we have, on the left side of the screen, we have the terminal portion of the project, where you can write code, enter it, get your return. And then on the right side, we have a code editor, which you can write longer programs in, hit run, and then the code executes. So I'm just going to do a little code right now. And so you can see there that we've got code executing on the left end with the terminal, and then we will also have code on the right side with the editor. And once I hit run, any kind of methods, classes, or other kind of programs I write will be stored in the REPL as state until you reset the reload the browser. And like I said, we have Ruby, JavaScript, and Python. And so that's the demo. I'm going to give a link at the end of the talk so you all can go try it out yourselves. But right now, just want to give an introduction. So collaborative programming environments are effective for remote technical interviews. It removes any kind of setup necessary for, let's say I want to collaborate with someone. We both want to try out Python. We've never used Python before. I have to download it on my computer. They have to download it on their computer. We have to go through our own individual configuration setup. And there's oftentimes some kind of debugging having to go through. With these kind of environments, instead you can just go to a URL and then just invite someone to your session and then just start coding away. However, right now, the current solutions outside of SpaceCraft are closed source or require user authentication. And right now, the 2 big players in this space are REPL.it and CoderPad. Can I see a raise of hands of anyone who has used either of these before? Cool, so pretty good room. It was actually a meetup last time where not many people had used either, so I'm glad to see a lot of y'all are familiar with it. But yeah, REPL.it, for a long time, all they allowed was for you to create a user account, and then you could write code in different languages. You can actually save that on your account, and it would just run in the browser. Although recently they released a kind of a multiplayer kind of version where you can invite other people to join your session. And then CoderPad, really popular with getting technical interviews, technical screens. You also have to sign up with an account. And if you don't sign up with an account, you only have like a 30-minute limit. And so, like I said, we wanted to make an open source alternative. We wanted to encourage developers to deploy their own version of this if they wanted to, just fork and go with it. But a big reason why we chose to is that once we got interested in this and we saw what went on behind the scenes of building it, the challenges were, oh, is that much better? All right, cool. All right. I don't know if I have time to go back to any, but we'll see. But yeah, as we dug into it more and more, the challenges of building the project just became very, very interesting. And so one of the reasons we built this was just to see if we could overcome these challenges. And so just to give you some high-level goals of the project, we wanted to enable a terminal-like interface for code evaluation for our 3 languages we support now. We wanted to allow multiple users to collaborate on the same REPL session. And then we wanted to synchronize displays so that the second anyone in the session types any kind of code on either the terminal or the code editor, everyone else in your session can immediately see it without really any lag. And then on top of these, we encountered these kind of challenges, which was we needed to isolate individual user sessions because we don't want anyone to join a session they weren't invited to. Because we have a terminal portion and it's connected directly into our backend of the project, we need to think about what about any malicious users who want to type something like rm or f and just delete all the file directory or insert any malicious code. And then we wanted to achieve real-time code evaluation and synchronization with no noticeable lag. And so just to give you an overview of how the rest of the talk is going to go, I'm just going to go at a very high level with the network architecture, then take a step down into more detail with building the actual REPL, and then lastly, getting into the nitty-gritty of our container architecture, which is how we address some of these security concerns, and then also how we connected users to sessions. So the technical requirements for our architecture was that we wanted it to be scalable. We wanted to be able to handle multiple runtimes. It needed to support, in our mind, 3 to 5 people per session minimum. It's good with 2 people in a session, but we wanted to have as much as a team working together. We needed to detect when a client disconnects to free up resources. And the reason why we wanted to do this was if we have a session and then all the clients leave that session, we didn't want new users to connect to that session, and then there's some leftover state in the terminal or other kind of artifacts they would have to deal with or erase on their own. We wanted to give them a new session. And so we need to know when all of the clients from a previous session leave. And then finally, we wanted to support bidirectional communication because there's going to be a high volume of traffic from users entering code, but then also output from code execution. And so we went with just client-server architecture, multiple clients connecting to a central server. It was the easiest form, and it handled all of our needs. And so now we get to this portion of the project of considering where do we execute the code? Should we execute it in the client side or the server side? And it's very enticing to do on the client side. Just have all of the computing done there, less lag, and just kind of offload it to the client. But we ran into several problems with executing code on the client side. We have the burden of running an in-browser compiler for the languages we choose to support, which potentially slows and hangs the browser. And it's also not scalable, because we found that the storage requirement for each language we support grows enormously over time. Right now, for each of our 3 languages, it's about 50 megabytes per language. And if we want to go on to add 5, 10 more languages, it's just going to grow out of reach for the clients. Also, not all languages come with an in-browser compiler, and that's not a task we wanted to take on ourselves in the future. And as some validation for this choice, this is an excerpt from an interview with Vincent Wu, who's the founder of CoderPad. And he said that, one day I sucked it up and I just realized that there was no way I could scale this completely in-browser execution as far as I wanted it to. What are you going to do? Compile every programming language into JavaScript? Good luck. And so since he's been there before and he chose not to do it, we chose to save ourselves some time and headache and not go about it either. And so we chose to execute code on the server side. It's easier to manage the multiple runtimes. It's also more scalable because we could either scale up by adding more server storage, memory, and CPU, or we could even choose to scale horizontally by adding more servers over time. The trade-off is, though, we have to manage those resources on our own. There is some increased latency between the client and the server for handling all that synchronization. And it is more costly for us, but we feel like this is doable, this is acceptable. So then we get to the part about how we handle all this communication and traffic between the clients and the server. And with HTTP, we have the request response cycle. And the header payload for each cycle is around 200 bytes. We wanted to do better than this. And we also wanted to have the bidirectional communication that I talked about earlier. And thankfully, a great solution for this is WebSockets. So with WebSockets, you have the initial HTTP handshake to connect the client with the server, but then a WebSocket connection is created, and then you have a full duplex persistent connection, and the payload drops to around 10 bytes, which we felt was just a noticeable improvement that we wanted to maintain. And so even on top of this lower payload, we have a larger number of persistent connections, and we have this last point, which was huge, which was that now we can easily detect when a client disconnects. Because with WebSockets, we have an event that fires whenever we have all of our clients disconnect from a session. And so instead of having to, with HTTP, possibly ping the client, see no one's there, and then tear down our session, we immediately have this event fire, and we can tear down our session and create a new one for a new user. So now we get to building a REPL. So typically, this is what happens on your local machine when you run a REPL program. Just you putting input through the terminal, and then your REPL program reads and writes back. But in our case, we have a more complex situation, which is that the user is sending input through the browser, and then it's going over WebSockets to our application server. And then it has to somehow send all this to the REPL program and receive output from the REPL program. But there's a missing piece here. And it involves figuring out how can we communicate between our application logic and our REPL program. And so we had a number of approaches on how we tried to solve this. First was to work with the language's REPL module. Node.js has a REPL module, and it allows us to just integrate that with our code. But the problem is that this just isn't scalable, because we would have to then work with all the other language REPLs, modules, and then that might be fine with the two languages now, but looking to the future with more languages, it's not scalable. So we don't have to rewrite our application logic each time we add a new language. So then we thought, okay, how about we access the standard streams of the REPL process? We can have our application spawn a REPL program and just write to the standard input and read from the standard output. But then we come into the problem of these streams can be blocked, and then we get some hanging output. And this just became a headache to deal with, and actually the techniques for solving this kind of issue differ from language to language. And so once again, this wasn't scalable to our needs. Yeah, I just went over that right now. So yeah, and the complexity would just increase with each language. So then we came to our third and final choice, which was to use a pseudo terminal. And here's that diagram again. And remember how I said there's a missing piece between how our application server speaks to the REPL program? Well, that's solved with the pseudo terminal, because a pseudo terminal will act as a communication channel between our application server and the REPL program. And the reason why this is because a pseudo terminal is a program that processes inputs and outputs to our REPL program. The big reason why we need the pseudo terminal is because a REPL program is a terminal-oriented program. It knows how to communicate with a terminal, but if you don't have a terminal in place, there's just not going to happen. So with a pseudo terminal, which basically tells the REPL program you're speaking to a terminal, it allows us to have this input and output with the REPL program. And so the advantages of this is that we get to offload the burden of managing this input and output with all the different runtimes. It works for all of them, and we can reduce our code complexity. It standardizes our way for the future when we add new languages. We can send control sequences like Control-C for in case you have a loop that you want to stop. And we can capture full outputs from the REPL program, like syntax coloring. But nothing's for free. We have a trade-off in that we now have another layer of processing to deal with. But so far in our testing, it hasn't produced any noticeable lag or performance issues. And so now we come to a quick little session about collaboration when you have multiple users and how that output synchronizes. So this is how it looks usually, where a client requests a line of code to be evaluated. This is very similar to what I did in the demo. The client sends some code to the app server, which then speaks to the REPL program through the pseudo terminal. And then the output is sent to the app server. And the app server then broadcasts that output through WebSockets to all the connected clients that are collaborating. And so then everyone's display is updated at the same time. So now let's talk about input synchronization. So now a user enters a key, like the left open square bracket, and we store that state on our line. And then we send that to the app server, notifying that a change has been made to the line. The application parses out the current prompt from the output cache just to give us that same consistent output. And then it broadcasts that to all the other clients. So this is happening with every keystroke you make in either the code editor or the terminal portion of the project. And then everyone's UI is synchronized accordingly. So now we get to our container architecture. So we have some problems to face when we're running our app within our host environment. And it's something that I said briefly before, which is we have this terminal that we're providing, and users can send code through it to our application server, but it's directly connected to our backend. And so there's the chance that a user can enter malicious code. It can be as simple as rmrf, delete your entire file directory, or it could be something even worse. So we have to figure out how to handle that. Another common case would be like a dirty cow or copy on write exploit. So there's that issue. And then there's also resource sharing. And so there could be a case where we have a couple sessions in play, and then one session, a user does some kind of program that's just more computationally intensive, and is just hogging all of the CPU, or it's hogging all of the memory that we have on the host system, and that just drops the performance for every other session. So if we don't handle that, then it's just going to have a poor experience for other users. And so we decided to use containers. Just a quick overview, because I'm not sure of the room how many have used containers before. But a container is basically an encapsulated single unit of software. It can contain an entire service. It prevents any conflicts with the host system, because you can then just deploy it anywhere. And containers are built from images, which are snapshots of all the dependencies inside. So you can see here, this is kind of how it looks like for this project. We have an image with all of our application source code, our language runtimes, and so forth. And then we create containers based on those images, and we actually create a container for every session. So now we have to talk about why containers. So like I said, we wanted to give some isolation between each session. We wanted to make sure that if I create a session, then I'm only able to allow people I want into the session. It's not some case where someone else can just randomly join my session. File systems are self-contained. Users will not have access to the host file systems. And the big thing is that containers have a lower footprint with memory than, let's say, a virtual machine. It's an order of megabytes to gigabytes. So in terms of how many containers we can run on a server, on a 4 gigabyte server, which is what we were using, we could run up to 100 containers. Not going to be able to run that many with virtual machines. While containers themselves aren't super secure by themselves, we can add measures to make them more secure. And finally, for all that resource sharing problems, we could add C groups to limit the usage. So I could say that each container can only use 20% of the CPU of the host system, and it can only use maybe 100 megabytes of memory for it. And so then no matter what anyone does in their session, they can't go over that, and the other sessions won't be affected. And so here you can kind of see just a diagram of what I'm talking about. We have 3 sessions in their own container. The middle one has been compromised. Maybe someone's running something computationally heavy, or they're trying to do some malicious code, but the other sessions are unaffected. There are still some more security risks to consider. One is that applications that run in containers can access system resources on the host system because they speak directly to the host system with system calls to the host kernel. Container escape is possible if someone's particularly crafty. So we had to then address these 2 issues. And so right now, as it stands, we have our app in a container, and then we have the host kernel, and there's a very weak isolation between the 2, and we want to address that. So the first step we did was we created a new unprivileged user profile and run that as non-root. So if a client is connected to the container, they're not going to have root access. They're not going to be able to enter rmrf or other commands we don't want them so we can limit their actions in the container. Next, in order to handle that isolation between the container and the host system, we can use a container runtime sandbox. And what it does is it gives some stronger isolation between the container and the host kernel. It intercepts all those system calls, and it acts as a guest kernel. So it provides unprivileged access in that case. The trade-off is with using the sandbox runtime is that we have some higher memory consumption. So in our case, when I said that we could run 100 containers on a 4 GB server, well, if we add a sandbox to each container, now we drop down to 50 containers. So, there is a price for improved security, and it just means that if you want to scale out, then you're going to have this limit of 50 containers, and that's when you have to add more storage, more memory, or you have to add more servers. But we chose to sacrifice this memory availability just to have some stronger security. And so here's that improved diagram with that container sandbox runtime. We chose to use gvisor, which is an open source runtime, sandbox runtime by Google. So really nice of them to create that for us to use. Not specifically for us, but they were out there. And so now we'll get to the last part of the project, which is we've got everything laid out. How are we going to connect users to a container? How are we going to get them into their session? So the naive approach is port forwarding, where we just take a user's request and then we forward them to the container by basically mapping them to the container's IP address and port number. So just direct one-to-one mapping. And you can see how that looks right here, where we have 3 sessions, we have our domain, and we have the port for that, and we have our container's IP and port. This is not great design. It's not a great design because these ports are predetermined, which means that anyone could access another session by just using a port sniffer, or even if they just started guessing port numbers and got lucky. There's very little privacy with this approach. And so what we did was we decided to add a reverse proxy. And so what a reverse proxy does is it acts as an intermediary between our clients and our server. It's going to abstract away the connecting of these URLs to the containers, and it's going to assign a random session ID as well to give us that extra just abstraction away. This ensures privacy of user sessions, and as the application scales, we can use the proxy to act as a load balancer as we get more servers, so then we can start directing requests to different servers to make sure everything's balanced. And so here's that updated table now, where each session has a unique session ID, and you don't have that port issue that I was talking about. And so here's how the flow works. The proxy server is going to receive the request from the client. It's going to relay to the server and get the IP address and port number for the container. And then through this WebSocket connection, it's going to set that up between the client and the container. And then when the last user in a container disconnects, then we can tear down the container. And yeah, here's just another image showing that between 3 groups of collaborating users, and they're all being forwarded to their appropriate container. And just to kind of talk about how this happens, with our reverse proxy, we actually communicate using the Docker Engine API. So when a user request comes into the proxy server, we then send an API call out, which initializes the container, and then we forward the request to that container. And then once all the clients are gone, a new call is made to stop and then kill that container. And yeah, and that's all I've got for you. That's the website for the project, as well as more details on everything, and also if you want to try it out. Thank you all for listening, and I'll take questions now if you have any. Yes. Oh, there is? Oh. Hello, hello. No, it's not on. Okay, cool. Appreciate it.
Thanks for the talk. Did you guys look at using WebRTC for client-to-client communication, or was it just easier to have everything go through a central server?
Oh, do you mean like doing like a peer-to-peer network?
Yeah.
Got you. We thought about a peer-to-peer network, but when we were kind of looking at the overall structure of it, it was pretty difficult to get set up. And we've actually known some other developers who did kind of a similar project. They made like a collaborative code, like a text editor with peer-to-peer. And they said, looking back, that it was just an enormous hassle to get over it. And so we decided, we have all these other challenges to take on, that a central server was just suiting our needs for us. Yeah. Any other questions? Yes. Oh, Mike.
Okay, yeah. So you mentioned that you worked with a remote team. How did you go about like putting together the people or finding the right people to work with?
Right. So we all just met in a Slack forum, and we just started talking, working on little projects here and there. And we were using CoderPad actually sometimes. We were just, hey, let's practice some code challenges or such. But like I said, CoderPad has that time limit. And you only get 2 pads, at last I used it, to save with your user profile. And so we just were kind of talking about this seems like something maybe we could make together. So to kind of talk about the workflow for how we work together, we used Zoom. I'm sure a lot of people have used it in their work, but that just enabled us to kind of video chat and bounce ideas off of each other. But yeah, it was just honestly kind of serendipitous. We just met on a Slack channel, talked, had similar interests, and just got to work. Other questions?
If not, I have another question.
Okay.
Where did you turn to for because you have pretty heavy duty security, or it looks like you obviously have or someone in your team had a background in it, or where did you turn to I guess look more into security?
Well, actually, none of us really had much of a background in security or even Docker beforehand. That just kind of came about as the evolution of the project. We built the REPL, we started going about, and then we kind of realized, oh, there's malicious code, people could enter into it. So it was really just a ton of research, just a lot of reading blogs, just reading case studies. The Docker or documentation was really helpful. That's where we found out about the C groups and also the root privilege access. So, just honestly, we researched a ton, and once all the research was done, the coding wasn't actually the hardest bit. So.
Thanks.
No problem. Do you have a question?
Hi. Do you guys support storing user sessions, and how did you deal with network issues and potential eventual consistency issues?
Oh, got you. So I actually had more slides on how we handle consistency, but the talk was over 40 minutes before, so I kind of moved it. But to give you a quick answer, for the code editor portion, we used Code Mirror, which is basically just a library that you can add that handles a lot of the conflicts for you. It uses a conflict-free data type, or CRDT, which is a really interesting CS topic, but it's really hard to build, and so we kind of just offloaded that to Code Mirror. And then for the terminal, we actually used the last write wins, because the reason we did that was we thought with the code editor, I could be working at the top, maybe someone else is working at the bottom on another class or something. We want to be working at the same time. But in the terminal, we didn't really see anyone fighting each other to write something at the same time. You only have one line, so we just figured the last write wins in that case.
Got it.
Cool.
Thanks.
Oh, you have a question? Can we get the mic over? Right here.
Hi, my question was more about the front end. Do you guys use anything like service workers to ensure that users have good offline experience?
So the question was if we use service workers to, what was the last bit?
To give a good offline experience?
Okay. Yeah, right now we don't have that, actually. We don't have anything for offline. It's something that would be great to look into, but we just don't have it right now. Yeah. Cool.
Awesome, yeah.
Yeah.
Thank you, Julius.
No problem.
If you guys have any more questions, will you be around after the talk? Or
Oh, yeah,
after,
definitely.
Awesome, cool, thank you. Ryan.